what's going to hurt my feelings. I turned off the audio. I probably don't even want to know it's going to hurt my feelings. Okay, so yes, we'll start recording right away. Welcome back, everyone. Yeah, this unfortunately I think is the less quiet of the mics. I mean, we can see. Oh, it is okay. Unfortunately, the better mics are these handheld ones, but oh well. Yeah, this is the quietest of the three mics that I have to use as I teach during the day. So in any case, today we need to bring it all home with chapter 11 with discussing elimination reactions. Oh, and by the way, just in case anyone comes late, no reef polling today. I'll try to get one done for Wednesday. Please just register your attendance. Please register attendance. Good, so we need to discuss elimination reactions today, of which there are three flavors to the two flavors of nucleophilic substitution reactions. Make sure we clarify those mechanisms. I also want to say a few things about Zaitsevs Rule. It's always someone's rule. It seems anyone with a rule named after them has to have kind of a Slavic or Russian sounding name like that, which I think is kind of interesting. And let's see. A couple other things I want to talk about, elimination reactions, especially in the context of cyclohexane derivatives, which I think will clarify a couple of things at once. And just so you know where this is all headed, I have, as you probably noticed in your class notes, I have kind of a flow chart that I've made, which is my attempt at organizing the information in this chapter. I want to be as clear as I know how to be. This is not the only way to do so, but it should at least let you guys get started with something. I will not be the slightest bit offended. In fact, I will be very pleased if you take the information in this flowchart and make your own, tweak it to your liking, because this is certainly not the only way to do so. Good, so let's go back to our whiteboard and double checking that I'm recording. Good, so let's see. Elimination reactions in general, we've already gone over, but there are three flavors of elimination reaction mechanisms. Two of them are going to be E1 and E2, and as we'll learn, those correspond real well to SN1 and SN2, a lot of similarities. So the E1 type elimination is going to start with the same type of starting material as for an SN2 reaction, except we're also going to require at least one alpha proton, meaning at least one proton on a carbon next door to the one bearing the leaving group. And just like in an SN1 reaction, the first step is that the leaving group leaves, unassisted by anything apart maybe from the polarity and hydrogen bonding characteristics of the medium, but that will give us a carbocation, just like it did with the SN1 reaction. So we'll get our trigonal planar carbocation. And then in the second step, some base, which we'll have around, is going to pull off that proton, use the electrons in the carbon-hydrogen bond to form a carbon-carbon pi bond and get rid of that plus charge on carbon all in one fell swoop. And we'll get an alkene as a product. And this is going to otherwise be very, very similar to the SN2 reaction. In fact, if you look carefully, you'll notice that first step is the same for both SN2 and, SN1 and E1. And that's going to have some consequences. One of the main consequences of that is that it will be very difficult in practice to separate between or to distinguish between SN1 and E1 products. Usually those two reactions will compete. and you'll get a mixture of elimination and substitution products. So just as with the SN1 reaction, this is going to be the slow step or the rate determining step. And the second step in comparison is quite fast. So again, I want to stress this, please be sure you're clear that this first step is the same as the first step for an SN1 reaction. The only thing that's different is we're specifying that there's at least one adjacent carbon with at least one hydrogen attached. But other than that, this is the same. You've got a substrate with a leaving group just like before. So this is not the reaction where everything happens simultaneously. Correct, that would be the E2 reaction, which is coming next. By the way, before we get to the E2 reaction, I would like to point out that the rate law for the E1 reaction will be just like the rate law for the SN1 reaction. Its rate is rate constant times substrate concentration. So the base doesn't enter into the rate law because it's not involved in the rate determining step. So this is a first order reaction, just like with the SN1 reaction. I would expect a very similar looking energy diagram as well. The only difference is we don't have that third step, which is technically not part of the reaction, but where we just need to pull off a proton in order to get a neutral product. That's not going to happen here because we've already got a neutral product. But other than that, it would be a very typical looking energy diagram for a two-step process. The E2 reaction, as you were just hinting at, is going to be a one-step process. This is going to be a bimolecular reaction. And just as the bimolecular nucleophilic substitution happened all in one step, so this elimination will happen all in one step. Our base, and we'll talk more about the base as to what it could be, how to tell whether you're looking at a base or a nucleophile. We'll cover all of these at least as much as we can today. But our base is going to pull off our proton, the electrons will shift in and form the pi bond, and we will lose the leaving group all at once. And we get our alkene as the major organic product. And yes, there are in all these cases additional inorganic side products. You'll get whatever the conjugate acid of the base is. Certainly your leaving group anion is going to be an inorganic side product also. If an SN1 reaction occurs, will the E1 reaction occur as well, like a racemic mixture? Well, in the case of an elimination reaction, there's no stereochemistry here because those two carbons are sp2 hybridized. So there's no issue of stereochemistry with an SN1 reaction, not like with an E1 reaction. But another question is, what if there's multiple possible alkenes that you can get? That's coming up. B means base. And the way it got there is we added it. We'll talk about how to know what's a good base and how to know based on what you're given, what you're going to be using there. But B stands for base because we're doing an elimination reaction, not a nucleophilic substitution. So instead of being given a nucleophile, you'll be given a base. Like I said, we'll talk, at least as far as time allows, as to how to know which you're being given. We'll get there. In any case, this reaction is only one step. So by definition, that's the rate determining step. There is only one step, so it must be rate determining. And so, just like with the SN2 reaction, the rate law for the E2 reaction is going to look exactly like that. Its rate is rate constant times base concentration times substrate concentration. So it's second order kinetics, and the rate law is second order. But other than that, it corresponds very well. But again, we get an alkene as the product, so there's no RNS type stereochemical issue. But there is one other possibility, known as the E1CB reaction. CB stands for conjugate base. So it's going to be a unimolecular reaction, but it's going to have a conjugate base in it, meaning something that's an anion. So conjugate base, let me just put that to anion. There's going to be some sort of anionic intermediate. And rate determining step means slow. That's right. The rate determining step is the slow step. The other step is comparatively fast. Good. So the E1CB reaction is going to be, in many ways, the polar opposite of the E1 reaction. And we're going to run into an interesting issue, which is how come there are 3 different elimination reactions, but only 2 types of nucleophilic substitution reactions? That's a question we're going to answer over the next few minutes. But in the E1CB reaction, we're going to go about this in exactly the opposite way from the E1. And if you look at the E1, I think you'll see that the first step has the leaving group leaving to give you a carbocation, and then we pull off an adjacent proton, an alpha proton as we call it, to make the alkene. In an E1CB type reaction, which we'll go over some ways that you can know that you're going to get one based on what you're given, in an E1CB reaction, we're going to do that in the opposite order. Instead of losing the leaving group first and then deprotonating, we're going to deprotonate first and then lose the leaving group. So as you can imagine, that's going to require a rather different setup in terms of the starting material. But in the first step of the E1CB reaction, whatever is our base that we're given, we'll pull off the proton, and rather than kicking out the leaving group, we're going to put those electrons onto the carbon and make a carbanion. So a carbanion. And carbanion intermediates are known. I think we've actually seen 1 or 2 of them already. And then in the second step, the carbanion is going to collapse, going to donate those electrons in between the 2 carbon atoms to make a pi bond and lose the leaving group. And you'll get your alkene. So what is the relative kinetics of those 2 steps? Well, remember, one thing we said about all proton transfer steps, any Bronsted-Lowry acid-base step, those are always kinetically very fast. Those are pretty much the fastest types of steps you can get. So this is going to be the fast step, and this is going to be relatively slow, or if you will, the rate determining step. You can write either RDS or slow. And you don't even have to write it unless the question says to, right? But I'm just putting that down just so that it gets into your notes and you're familiar with the information. But it's a 2-step process, except it goes in exactly the reverse order of the 2 steps in the E1 reaction. So instead of losing the leaving group first, we deprotonate first, and we get a carbanion. That carbanion then collapses, we lose the leaving group, and we get our alkene. So now it's this step that's the rate determining step, and it again involves only 1 species. So it's again a first order rate law. I'd expect it would be the same as the rate law for an E1 reaction, because you're only going to get this conjugate base, this carbanion, from a substrate molecule. No other species are involved in that step. So your rate is still going to be rate constant times substrate concentration, since substrate concentration and concentration of this stuff are going to be proportional to one another. Because you're not going to get this anion except from a substrate molecule. And again, I don't see anything else mentioned in this mechanistic step. The base is not involved. The base has already done its thing. So we again have a first order reaction, but it's the E1 reaction flipped on its head. So before we go into some examples, now I can ask what I mean, maybe it's just me. I think it's an interesting question. It's one I often get asked here. It's one I bet you're all thinking of, which is, so how come there's no SN1CB? How come there's only 2 types of nucleophilic substitution reactions, but 3 types of elimination reactions? And I think if you consider what you would need to have in order to get an SN1CB reaction, you will immediately see it's impossible. How did we go from E1 to E1CB? Well, we switched the order of the steps. Right, instead of losing, I'm pointing with my fingers, though people can see that on the screen. You're starting with loss of the leaving group to give a carbocation, and then you deprotonate. And to turn that into E1CB, we flip those steps around. We deprotonate first with our base, and then we lose the leaving group. So what would this putative SN1CB reaction look like? Well, what's an SN1 reaction? In an SN1 reaction, it's the same first step as for an E1 reaction. We lose the leaving group. And then in the second step, the nucleophile attacks that carbocation and we form the product. So, or the nucleophile attacks and we form the product. So somehow we'd have to reverse those two steps in order to get this strange beast known as an SN1CB reaction. The nucleophile would have to attack first without loss of the leaving group, and then the leaving group would have to leave. And if you have just your nucleophile attacking that substrate, and the leaving group hasn't left yet, now carbon has 5 bonds, and that's impossible. So that's why you can't have an SN1CB reaction. There's only 2 types of nucleophilic substitutions. Can you choose which method is used in lab, or do they all happen together? Well, some of them happen together, and it's pretty hard to avoid that. Others you can choose to at least heavily weight one over the other. And like I said, we're going to see some examples of how you can know that, how you can know which to expect in this flowchart. So if you wanted E1 products, would you just use E1CB? One thing about elimination reactions in general is generally the product's the same no matter what. You're going to get an alkene, so pretty much no matter what the mechanism is. But you can choose which mechanism you'll get. And the reason you might want to do that is because you might be doing a kinetic study. Actually, I'm going to give you an example later whereby carefully selecting the reagents and the solvent, we can pretty much guarantee that we're going to get an E2 elimination. So we'll talk about that. I can't give it to you all at once. We'll go step by step, and I'll show you how you can select for one reaction over another. But these are the 3 types of elimination reactions: E1, E2, and E1CB. We'll go over examples of all of them. And again, at least as time allows, we'll go over how you can know which is going to happen. Good. So that's pretty much the general scheme. Any questions on sort of the generalities here? We'll do specific examples, but I just am wondering, are there questions about the general cases here? And I love the questions. The questions are exactly the right ones, by the way. You know, how do you choose which one that you get? And little by little, one by one, we'll get to that. So let's see. One idea that applies regardless of the mechanism, though, regardless of whether it's E1, E1CB, or E2, regardless of that, we have to ask the question, what if multiple alkene products are possible? How do we know which to put down as the major product? Since often that's what we're asked, draw the major product, right? And that, what's going to help us out there is something called Zaitsevs Rule. Z-A-I-T-S-E-V. And I will write it down, but just let me say it first. But Zaitsevs Rule I don't think is going to come as a surprise to anyone here. Zaitsevs Rule simply says that if you're in a situation where more than one alkene product is possible, and I'll show you how you can know that you're in such a situation, but if more than one alkene product is possible, the major product is going to be the most stable of any or all of those alkenes. Period, full stop. The major product of an elimination reaction, regardless of which type, regardless of whether it's E1, E2, or E1CB, of an elimination reaction, will be the most stable possible alkene. The most, looks like some of our screens are cutting out. The most stable possible alkene. And how do you know which of 2 or more alkenes is the most stable? Well, we talked about that in chapter 7. So please review chapter 7, section 6, if you've forgotten how to do that. There we gave an order of stability of alkenes. And the very short form of it is the more substituted the alkene, the more stable, other things being equal. There are a few other things in there as well. But that's how you know which of 2 or more alkenes is the most stable. We went over that in chapter 7. So please do review that if you've forgotten that. You have to know that in order to be able to apply Zaitsevs Rule. And an example of Zaitsevs Rule is, let's say that we had this starting material. And let's say that we treated it with some strong base, maybe, let's say, sodium ethoxide in ethanol, though it doesn't really matter. Well, I think you'll discover that there's two possible products. One of the products looks like this, and the other product looks like this. And we'll go over how you can get those two structures. We'll go over how you know that those are the structures. But before we do that, I just want to point out that Zaitsevs Rule says that of those two possible products, the major product is going to be the alkene that's more stable, and that's this one. That alkene is tri-substituted, this one is only di-substituted. So that's going to be the major product. The other one will only be a minor product. To what degree, what's the exact percentage of each? I don't know. I don't have any exact experimental numbers memorized. Since they go through a carbocation intermediate, that's a good point. Remember, this student has the red flag working in his head. Remember, if we have any mechanism that goes through a carbocation at any point along the mechanism, that red flag should go up. Look out, we might have carbocation rearrangements. So yes, that's going to be the case, especially if our substrate is secondary. So just like with the SN1 reaction, we do need to worry about the possibility of carbocation rearrangements. But here, regardless of the mechanism, if I had to guess, I think it would mostly be E1 because of our protic solvent, though there might be some E2 in there as well. Not that it really matters because the products are the same regardless. And that's pretty typical for elimination reactions. It's very often the case, if not always the case, that it really doesn't matter what the mechanism is, the product's going to be the same. It's just a question of being aware of what the mechanism, the kinetics of the situation are. So how do I know that those are my two products? Well, the way I know that is because there's two types of hydrogens that are next door to the carbon bearing the leaving group. That's one that I've colored in using red. The other one is over here. CH3, I've written CH2H. So you can see there's three hydrogens of that type. And losing the green hydrogen, losing the green proton will give one of the two products, and losing one of the red protons will give you the other type. So let's see how that works. Let's go ahead and lose one of these red protons first. So, and again, I think it's reasonable in this case to guess that the mechanism will be largely E1. So that means in the first step, we just lose our leaving group. We'll get this carbocation, and then our base comes along. So how do we know what the base is? Well, let's look at what we're given. I'm given sodium ethoxide and ethanol. And so I'm hoping that you're aware that this means that the base is ethoxide. Right? Remember, anions are often given as alkali metal salts. So NaOET or ETONA is ETO minus. That's really important. You guys have to know that in order to understand so many things, that the sodium cation plays no role in the chemistry. And the way you know that is if you go back and look at the mechanism, you'll see no mention of it. There's no way we can draw arrows with using an alkali metal cation. So this is going to be our base. That's going to pull off one of these protons, and we'll get, in this case, the major product. And of course, if we had pulled off instead one of these two over here, it gives the same thing. It doesn't matter if you draw the double bond here or here. It's the same compound. You've just turned the molecule. So losing one of these red protons is, in this case, how we get the major product. How do we get the minor product? Well, the first step is going to be the same. I could quibble with my bond angles here, but be that as it may. Instead, we'll take away one of those protons in that methyl group. All three of them are the same. But after the first step, we get the same carbocation. And now in comes our base. Oops. So along comes our base, same thing. That's going to pull off one of these protons. And now we will get, I'm going to be lazy, we get that compound. So this is the explanation of how we get those two compounds. But Zaitsevs rule helps us to predict what's going to be the major product. And to, I'm sure, no one's surprise, the major alkene is just going to be the one that's the most stable. I think we'd all be kind of surprised if it were the other way around. So as always, I'm more interested in you knowing the idea, which is that if you have multiple possible products, the major product's going to be the most stable one, than that you know it's called Zaitsevs rule and how to spell that, for instance. In other words, if I have my choice between those two things, I'll take the first thing rather than the second. So it's important for you to be able to apply the idea, that given even a situation and a set of structures that you've never seen before. That's what we need to aim for. Good, so other than that, that's basically Zaitsevs rule. And in this case, I think I'm on pretty solid ground predicting a largely E1 situation, but whether it's E1 or E2 or E1CB doesn't matter. Zaitsevs rule applies in all cases. And again, to I'm sure no one's surprise, we would expect to get as a major product the most stable of all possible alkenes. So you need to know how to identify which protons you'll remove. And so you need to be able to say, well, my leaving group is attached to this carbon, and so all of these three carbons have protons that could be removed by a base. And so you need to know how to do that. You need to know to look at the next door carbons. Those are going to be the protons that can get removed by a base in order to do an elimination reaction and make an alkene. Good, can't really think of anything else other than that. Any questions on Zaitsevs rule then? Possibly, because what is stopping the ETO minus from adding to the carbocation? Well, it could, of course. I think ETO minus is a pretty strong base and probably likelier to do that. Sorry, I'm just blanking out for a moment. One of the things that I'm going to let you guys know as part of that flow chart that I gave you guys is generally, if you're looking at generally your strong bases are going to be like hydroxide or NH2 minus. It would be a tad hindered, but we're going to come back to the idea of alkoxide ions as nucleophiles, though, in chapter 18 when we get to ethers. We're going to learn that you can make an ether very easily by nothing other than an SN2 reaction. And so I'm hoping between that chapter and this chapter to help you guys to disambiguate that so that you can know what's going to happen based on what you're given. But I think here, especially with the structures that we have here, I think we can expect ethoxide to add as a base. So another way to answer your question, which is not dumb, by the way, not dumb at all, is I think you'll be able, at least for starters, to use the flow chart that I've given you. Maybe, again, tweak that to your liking. And that will help you to decide which you're going to get, or at least what you're going to get the most of. So all these things put together, first of all, make a pretty broad base of knowledge, but admittedly, there's a lot of details there and it's a little bit complicated. So that's why I've given you that flow chart, just to help you out, at least in beginning to organize all of the information. So I want to be sure that I leave at least, say 5 minutes to go over that flow chart at the end of class. Good, so there's 2 other issues that I want to talk about. I lied, 3 other issues. And actually, since we haven't really seen any E1CB mechanisms yet, I haven't given you an example yet, I thought I'd at least give you one where we could be pretty sure that it's going to go by an E1CB type mechanism. So there's that. I also want to talk a little bit about the deuterium isotope effect, and in general, the effect of heavy isotopes as opposed to light ones. And time permitting, I want to talk a little bit about the anti-periplanar geometry, especially as regards cyclohexane derivatives as substrates, since it's the easiest to see with those. And then hopefully there'll be remaining time for me to go over this flowchart a little bit with you guys. Good, so let's clear all that. So what would be an example of an E1CB reaction? Well, one of the things you'll notice in the flowchart, in fact, in the version of the flowchart I gave you, it's pretty much the first decision you'll make. Right at the beginning, we want to figure out in that version of the flowchart whether we're going to get an E1CB reaction or not. And in general, we can probably figure out what we're going to need. So somehow the first thing that's going to happen in an E1CB reaction is deprotonation. Stands to reason we probably are going to want a really strong base, something at least as strong as hydroxide. And since the leaving group doesn't leave until later, maybe we would expect that the leaving group would be kind of bad in order for us to get an E1CB reaction. And so that's normally what I look for if I'm trying to find an E1CB reaction in the wild. So let's see, if I were to give an example of an E1CB reaction, I would want to load the system up something like this. How about hydroxide? That's a pretty bad leaving group. And what if we were then going to treat this with sodium hydroxide in ethanol or water or something like that? This, I think, would be a pretty good setup for an E1CB reaction, in part because of something we won't learn in full until next term. But next term, we're going to learn that protons on carbons that are next to a carbonyl, like this one, like these here, are slightly acidic. And we'll learn why that is, next term, although I think you're about to get a hint at it just from what we're going here. But here we've got a bad leaving group and a strong base. So, and again, that's in the flow chart. So, wait a minute. So I think this will give us the best possible likelihood of getting a largely E1CB mechanism. Question or no? Okay, well, let's go through the mechanism and hopefully it'll clarify itself. But we did say the other day that hydroxide is a bad leaving group, and we talked about why that was. We gave order of leaving group abilities. And so I would expect this to go through an E1CB type mechanism. So in other words, that first we'll pull off one of these protons, we'll put the electrons in the CH bond onto that carbon, and so we'll get this carbanion. Of course, the other H is still there. We just pulled off one of them. But that's another thing, by the way, that if you look at this intermediate, this carbanion intermediate, I bet you can figure out why those protons are slightly acidic compared to other CH bonds. I think you'll be able to find another resonance contributor for this structure, one that is the minus charge in oxygen. And we'll of course cover that in full next term. We don't really need to go there just now. But I mention that in case some are curious why I'm pulling off a CH bond all of a sudden. So we do get this carbanion. This, of course, would be the relatively fast step. And then in the second step, the carbanion will collapse. The electrons in that lone pair are going to be used to form a pi bond, and we break the bond to the leaving group, which is admittedly a pretty bad leaving group. Hydroxide's one of the worst leaving groups there is, next to maybe like, I don't know, carbanions. It could get worse still. But in any case, I would expect our product would be methyl vinyl ketone, which looks like this. And there's, of course, inorganic side products as well, but the major organic product would be this alkene over here. So that's an example of how you can know that you're going to get an E1CB mechanism and how you would show it. So, and again, you'll see that right at the way I've done your flow chart, it's right at the very top of the flow chart. But I did want to be sure that I gave at least one example. But you want to look for, you know, anything that you can do to make those hydrogens a little more acidic. You probably want a strong base, one at least as strong as hydroxide. Stronger would be even better. And you want a bad leaving group, hydroxide or alkoxide or fluoride maybe. That's going to give you the best chance for an E1CB reaction. So that's how you would draw a typical E1CB mechanism. That's just one example. But again, but just as with all other eliminations, we're going to get an alkene as the product. Yes. The OH attack the other carbon. You mean this over here? I'm still not sure what you mean. These, you're talking about the hydrogens over here. Oh, this one. No, those hydrogens are not acidic. Oh, do you mean attack it and displace hydroxide? If it does, then you get the same thing again. If OH minus attacks this and kicks out hydroxide, you get the same thing back. So there's no consequence if that does happen. I don't think it would very much. But yeah. Good. Other questions then? All right, well, from here, let's talk about the deuterium isotope effect, or I almost just want to say heavy isotope effect. Your book mainly mentions deuterium, but there are other heavy isotopes possible, and that's why if you look at the old exam, the practice exam, you'll see instead of hydrogen versus deuterium, I went with bromine 79 and 81. What needs to be more acidic? I'm not quite sure what you mean. Did I say a little while ago that something needs to be more acidic than something else for something to happen? I'm not clear on the question. Well, while you ponder that. The idea of heavy isotope effects has to do with the hydrogens next to the carbonyl. Are you talking about the comparative acidity here? You said look for ways to make something more acidic to know if the reaction is E1CB. Well, this is one, and I just told you one. Other things that will make the hydrogens more acidic that you need to know might be if there's an electronegative atom nearby that's going to withdraw electron density and make the carbanion more stable. So we've talked before about effect of structure on pKa. So that stuff you still have to know, I would say, and applies to this kind of information. So if you want to know what to look for in order to make a hydrogen more acidic, please go back and review that material. We've talked about effective structure on acidity to some degree before. Good, so hopefully that helps. So what we find is that it matters what the isotope of an atom is when you break a bond to that atom. And I'm going to write this down, but just let me say it first, which basically is that other things being equal, an involvement of a heavier isotope of an atom in a rate determining step will slow down that step compared to a lighter isotope. So I'll put that down. Let's see. Bonds to heavy isotopes break more slowly than bonds to light isotopes. That's about as succinctly as I think I can put it. So often this is done by making a comparison between deuterium and hydrogen. So one easy example, well, let me not use pH. One example that comes to my mind, let's say that we had this starting material. I'm sick of chlorides and bromides. Let's use a tosylate. And we treated this with, let's say, sodium hydroxide. And just to make sure that we get an E2 elimination, why don't we make the solvent DMSO, dimethyl sulfoxide? And the product that we'll get in this case would be styrene plus inorganic side products The mechanism, fairly obvious. Here's our base. Remember, NaOH means OH minus. That's going to pull off one of those protons. We're going to use the electrons in the CH bond to make our pi bond and kick out the leaving group. Especially with that polar aprotic solvent, there's no way we're going to get a unimolecular reaction. Which again, that's one of the things I also gave you on that flow chart. If you've got a polar aprotic solvent, you've just put your thumb on the scale, so to speak. You're not going to be able to get a carbocation. Those are not stable in polar aprotic solvents. So you would more expect a bimolecular reaction. So that's fine. And of course, that other hydrogen's still there. Let's say that we compare this to the starting material with deuteriums in that same place. And we've gone over what deuterium is, hydrogen 2. Well, that can still be pulled off, right? Instead of pulling off H+, we'll pull off D+. We'll again form the pi bond with those electrons and kick out our leaving group. So now our product is going to be the same thing, but with one deuterium in that position. And so what the effect of heavy isotopes means is that this step will be slower and this step will be faster. Or rather, this reaction will be slower and this reaction will be faster. Not because of the structure of the product, but because of which isotope we're pulling off. It's faster to break this CH bond than it is to break the carbon-deuterium bond. And the reason for that, by the way, would, as with so many things, require heavy-duty quantum mechanics. There's no simple low-level explanation of that. But other things being equal, when you're talking about bonds that are breaking in a rate-determining step, substituting the atoms with heavier isotopes will make the step slower. And with deuterium, it can be very dramatic. It can be a difference of 5 to 10 times or even more. Now, to give you an example of how you can know that nothing of the sort is going to happen, let's say that instead we put our deuterium over here. And you can draw the mechanism out. The mechanism's the same. Well, the product would still have that deuterium over there since it's not involved in the reaction at all. So now there's no deuteriums involved in the rate determining step. This deuterium is on the other side of the molecule. It's not involved in this bond breaking over here, right? The base pulls off the proton. That's way over here. And this deuterium out here has nothing to do with that. So I would expect this reaction to be pretty much the same rate as this one. Maybe not exactly, but pretty close. So do you see how you can tell whether the heavier atom is involved in the mechanism of the rate determining step or not? And again, how do I know that's the rate determining step? Because E2 has only one step, so it must be rate determining. Right? So all that comes together all at once. Good. Well, I'm left with 2 minutes. I still really want to, you know what? I still really wanted to talk about the cyclohexane situation, but I don't think 1 or 2 minutes is enough for that. So I think, as I've been doing so often recently, I think I'll use your lecture, but I'll append some stuff from the previous lecture. Before we do that, though, I want to at least show you, if nothing else, this flow chart that I've made for you. So this is a good starting point, but I do want to stress this is not the only way to organize the information. Here I started with these questions here so that we could eliminate, or not, as to whether we're going to get an E1CB reaction right up front. And then the rest helps us to distinguish between substitution and elimination. And if it's elimination, E1 or E2, if it's substitution, SN1 or SN2. You'll notice that often these reactions will compete. So often you'll get a mixture. And again, you'll get some ideas of question formats and what to put down in order to get credit from not only my old exam, but also the OWL assignments. I will say, though, what I really want to end with is this is by no means the only correct way to write down this information. And I would certainly encourage you all, Oh, you're right. I keep forgetting it's until 50. It's my other class that's until 45. Thank goodness. Okay, well that will maybe mean that I'll get a chance to go and give an example with a cyclohexane derivative, since those I think show us a couple things. So I'll just mention my other point over here, which is you could very easily, and I would encourage you to try. Oh, question. Right. We went over how to know whether a leaving group is good or mediocre, or a nucleophile is good or mediocre or excellent in one of the previous classes. We gave an order of the different ones and how reactive they are. So, but yeah, I mean, it takes practice. It's not something that you're given straightforwardly. But I still think that at least gives you some place to start. But what I was saying was, you could very easily make a flowchart like this, in which the question you started with involved looking at the solvent first. I made that point just a few minutes ago. If you've got a polar aprotic solvent, if your solvent is DMF or DMSO or maybe even acetone, you're not going to get SN1 or E1. You're going to get a bimolecular reaction. There's no way you're going to get a unimolecular reaction, because polar aprotic solvents cannot stabilize carbocation intermediates. So regardless of all the other stuff, if you see a polar aprotic solvent, I always look first for an E2 or an SN2 reaction, because I know I'm just not going to be able to get a carbocation intermediate. Good. So I think that's all. That will at least get you familiar with that. That leaves me now 3 minutes to still a little bit tight, but that at least allows me to give an example of a cyclohexane type intermediate. Let's say that we're looking at, yeah, let's do it this way. I would really like to say that we're starting with something like this. Attendance, yeah, it's up here. We're taking attendance. So if you haven't registered your attendance, please do so. Let's consider the other chair form before we go ahead and treat this one with a base. So it's been a while for me too. I'm going to grab this nose and pull it down, grab that nose and pull it up. So everything's going to seem to go counterclockwise. That means my isopropyl group will be up here, hydrogen over here, then my chlorine will be over here. Yes, I like this example. This example pleases me. Yes. Okay, so let's say that we took this guy and we treated with some strong base, hydroxide, ethoxide, what have you. Maybe even we'll use DMSO as a solvent just to put our thumb in the scale and make sure that we get an E2 elimination and don't have to worry about forming any carbocations. The question then becomes, which of these two chair forms is going to be the one that actually reacts? The answer is we want to look for the formation of, we want to look for anti-periplanar geometry. That's always going to be favored in an E2 reaction, which simply means that the proton we pull off in the leaving group need to be 180 degrees apart. So H and leaving group are 180 degrees apart. And for best results, we need that type of geometry. So here's our leaving group, this chlorine over here. I don't see any of the adjacent hydrogens as being 180 degrees apart. Actually, it looks like about 60 degrees apart. But over here, now we can lose that leaving group and pull off that proton. Those are 180 degrees apart. And so when we treat this with our base, again, I'm just for the sake of argument, I'm going to say sodium ethoxide in DMSO. Well, it means that our base is going to prefer to react with this conformation. Pull off the proton, the leaving group is then 180 degrees apart. And so the result that we'll get, if you work it out, our isopropyl group is going to be up here, and the double bond's going to be over here. So the reason I'm not drawing that as a chair is because cyclohexene is not a chair any longer. As soon as you put a double bond in the ring, it flattens out that part of the ring. If you really want to know what kind of shape it has, I don't know that I really care if you memorize it. It would probably be something like this. But it just flattens that out over there. But with, oh, no, I had until 12:50, so we're just finishing up now. This is good. So that being the case, you can see the stereochemistry of the product that you get. Even though the starting material looks like those two are trans, right? Unless I've totally lost my mind. Looks to me like the isopropyl group is up and the chlorine next door is down, right? Something like this. So these two are the same and those two are the same. So bottom line in terms of what you have to know for this step, for this idea, is by all means possible in an E2 elimination, you want your leaving group and the proton that you're pulling off with your base to be 180 degrees apart. It's pretty easy to see whether you're going to do that on cyclohexane. So I would say if you've forgotten how to draw chair conformations, probably a good idea to go back and review that, because that will make a lot more sense. And which two won't happen with polar A protic solvent is the ones that go through a carbocation, E1 and SN1. You're not going to get a carbocation intermediate with a polar A protic solvent. And other than that, I'm out of time. So on Wednesday, we'll start, I believe, chapter 17. That material will not be on exam 4. That'll be on the final exam. So have a great day, and I'll see you all then.